Yeah, thanks to the organizers for inviting me. I hope everybody can hear me online too. Also, I'm not a mathematician. I'm a physicist. Thanks for your tolerance. In fact, I'm a hybrid. I mean, my background is theoretical physicist doing statistical mechanics in biology. And as a postdoc, I became interested in evolution and have begun doing experiments. The first experiment worked, and then I wanted to have a wet lab. And that's what I have now. And I realized not always do experiments work and have to be repeated many times. All right, but today I thought I talk a bit about theoretical projects that we have done over the last couple of years that involve jackpot events. I will explain what I mean by that. Essentially events that cause populations that undergo kind of evolution to look as if they have a very broad offspring distributions. And as a consequence, it gives rise backward in time to multiple merger coalescence. What we are interested in also in particular is trying to develop a forward in time approach where we can also implement selection, which for evolution is very important. And by the way, please interrupt me with questions. It's always much more lively if one does that. And I'm sure this is going to be boring if there are no questions. I don't have to get to the end for that. Still need some kind of pointer. Is there a wooden stick or something like that? No. For most of the talk, I have one setup in mind, and it's a very classical setup where we consider a population which consists of a wild type, and then a mutant is coming in by means of a mutation. It could also be a migration event. Think, for instance, SARS-CoV-2. We are in the Delta world, and suddenly Omicron comes along. Then, well, Omicron has on average a larger number of offspring, number of infected individuals. So we expect it to rise kind of exponentially, and we want to model that. And the simplest way to do that is in this way. Here I'm describing with capital X the fraction of the mutants over time, and the rate of change of that is increasing when X is small exponentially with a rate S, where S would be now at a rate S, which is the growth rate advantage of the mutants, and then it saturates at 1. But of course, that's certainly not the entire story, because the infection process is quite random. And so there must be some version of genetic drift, some kind of fluctuations, conventionally modeled in this way by a diffusion term. So by a diffusion term, which is the one that I'm displaying here, which for small x has a prefactor such that the variance is additive in the number of mutants as if they are independent from one another. But of course, there's also a 1 minus x term because you cannot go past x equal to 1. And with that noise term, if you simulate this, well, one of the really quite salient insights is if you start with just one mutant, most of the time it will go extinct if this little s is small. Omicron is not a good example for this case. But often in evolution, we would think beneficial mutations have a small fitness advantage. So most of the time they go extinct and they take off only with a probability of order S. All right, of course, in this, well, this is kind of Wright-Fisher or biased Wright-Fisher diffusion, the model that I depicted here. Of course, there are some strong assumptions involved here about how the world behaves. First of all, selection. We've assumed here that this is kind of taking off exponentially. That might apply in the SARS-CoV-2 context if you think about one city like Montreal. But if we have some spatial structure, then we can't really expect selection to work like this, giving rise to exponential growth. Also then, these fluctuations in the number of infected are assumed to be uncorrelated among individuals. That's also often an approximation, like for instance, if in Montreal there's a conference, a math conference, and somebody has COVID, if I had COVID, for instance, then there would be a lot of correlated events, which is certainly not in this math term here. And also that what's assumed here to be able to describe these fluctuations by diffusion is that the offspring distribution is sufficiently narrow. And also for SARS-CoV-2, in fact, we know there are super spreaders that presumably have a rather broad distribution of offspring numbers. So in fact, this is, I would say, more generally the case, and one of the bigger problems in the field, that often populations show some kind of self-organization represented in, for example, their spatial structure, the way they form. Here, these are microbes that form biofilms, which have elaborate structures, or even somatic cells, us, which are animals formed from a single cell. We have an elaborate body plan, which is somewhat boxing in the way evolution can work. And this is very poorly understood. In general, my lab tries to understand this a little bit better in combination of experiments and models. Today, I want to focus on this last point here on what I call narrow offspring distribution. I want to point out today that often in models, we like to think about traveling waves, in particular, jackpot events emerge from the combination of mutations and growth, and they heavily impact evolutionary dynamics. We also try to understand additional, specifically spatial mechanisms of forming jackpot events, but I probably won't get to that, but I have a backup slides if I happen to have enough time at the end. Right, so the term jackpot events first came in by seminal work due to Luria and Delbrück in the 1940s, presumably during a faculty dance event. Luria realized watching a colleague playing the slot machine, that person seemed to be very lucky in that moment. He realized that the mutations he sees in his experiment could also be lucky in the following sense. So in his experiments, Luria grew bacterial populations from more or less one cell. And he realized if a mutation occurs during this expansion process very early, then a lot of mutants would be produced. For instance, here we have still a small population of just cells, and imagine one of them becomes a mutant, and now the population expands. Then also this mutant population will expand and form a large clone or family, however we want to call it. And he called those events jackpot events. And so he passed this insight on to Max Delbrück, who then mathematized this insight. There's a lot of complicated math you can do, but really, if you think about just the clone size distribution or family size distribution, conditional on one mutation entering the population, it's relatively straightforward. I try to indicate it here. If a mutation occurs in the second cell, then we expect about 50% of the final population to be mutants, right? Because each of those cells are then expected to grow at the same rate. If the mutation occurs in the third cell, well, we expect 1/3 to be the final frequency. If the mutation occurs in the n cells, we expect 1/n to be the frequency in the final population. And by this argument, you can easily convince yourself that, well, conditional on one mutation entering this growing population, the probability that the final fraction is larger than little x should go like 1/x. So that's a rather broad distribution of mutant frequencies. And in fact, if this wouldn't have any cutoff, this frequency distribution, it would have a diverging mean and variance. So in fact, of course, there is a cutoff set by essentially the population size. And so Delbrück realized if mutations are happening spontaneous in our experiments, I should see a lot of fluctuations in the mutant numbers from experiment to experiment. The variance would have to be very large. And that's indeed what they observed, and was provided evidence that mutations are spontaneous. It doesn't rule out that there are other types of mutations, and therefore there's still a lingering debate about spontaneous mutations and induced mutations. But I think much more fascinating about these jackpot events is that they actually occur when we think about other models, especially models of traveling waves. They can easily occur and continuously, and that's what I'm trying to illustrate now.
Excuse me, Oskar.
Yeah.
Can I ask a question?
Sure, absolutely.
Why would the probability of having a mutation in the nth cell to be 1/n?
No, this is, suppose one mutation, we know one mutation enters this growing population, right? Randomly, the mutations occur during cell divisions, right? We have to grow n cells, we need n cell divisions, and they randomly occur in this one mutation occurs randomly during one of these n cell divisions. If the mutation occurs in the nth cell that's being produced,
yeah,
then we have, at that moment, we have n-1 wild type and 1 mutant cell. Now imagine all of these are growing, then I expect the final frequency of mutants to be the same as it was when the mutation occurred. So 1/n.
Yeah, I understand.
That's what this means.
Right. But then on the left, you have the probability that the mutant fraction is greater than x is proportional to 1/x. So I don't see how this follows from that.
Right. So here we assume that mutation, like conditional on one mutation occurring, can occur during any of these 1 to n cell divisions. Maybe it's good actually if I here. So suppose here's our first cell, and here I have an axis just indicate numbers of cells produced and so on. So this is kind of on a log time scale, right? So if here a mutation occurs, expect the mutant fraction to just stay the same, 1/3. So if you want to know what's the probability that the final fraction is larger than little x, this should be equal to the probability population size at which, so that the mutation that the population size at the time where the mutation occurs is smaller than, sorry, I shouldn't call this capital N, I guess. The mutation occurs at a time, let's say, n star smaller than little n of x, and that's just proportional, or that is given by essentially n of x divided by capital of n, because I have n cell divisions to generate capital N cells. But n of x, right, the population size, the largest population size at which the mutation can occur so that the final fraction is equal or larger than little x, scales like, or is actually 1/x.
Yeah.
So I need to think about your equal signs, of course, but the scaling is clear from this. Okay. Any other question? Okay, so now this broad offspring distribution actually occurs. No, sampling from this broad offspring distribution actually occurs repeatedly if we think about traveling wave models. That's kind of the next step that I want to discuss. An experimental example you might have in mind is the long-term evolution experiment done by Richard Lenski, who now for over 30 years propagated E. coli in flasks, like every day. He dilutes the population and adds fresh medium, grows up the population and so on continuously until today with very few interruptions. There are 12 lines, and these 12 lines have now increased in their fitness over time, like this. There's a lot of findings, empirical findings from this experiment, but it also sparked models to try to understand what's going on here. And the salient one, or the simplest one also, is one that involves traveling waves. In fact, it's more like a traveling pulse along the fitness axis. And I think Jason Schweinsberg is describing the math and rigorous results about this model. So what you find in this model, essentially you have a Gaussian looking distribution, at least, over fitness space, where here in this model, one assumes that every mutation has the same effect, little s, right? So you have discrete classes here, bins, 0s, 2s, and so on. And the total population size is constant, so that in such a situation, you have typically growth in the bins that are more fit than the mean, and you have reduction and shrinkage in the other bins so that the total population size stays constant. Now, if we, and one of the findings is that the speed goes like the log of the population size. But now, where is this Luria-Delbrück effect? It happens really at the tip of the wave. First of all, you have there, let's say before this bin even arises, you have a population that's growing exponentially. And in this population, mutations are occurring. If a mutation occurs, it generates an entry in the next bin, like a lineage in that next bin. And these mutant population is also growing. It's growing at a slightly higher rate than this one, which kind of modifies the picture slightly. But still, at the edge, or let's say the edge of the wave, as you create the foremost bin in this traveling wave, you repeatedly sample again from this very broad distribution where the exponent has a correction of order 1 over log n. And you sample from this distribution actually at a rather high rate, 1 over log n. So in one coalescence time, you have many such resampling events. And so essentially, if one can define effective, well, before I say that, I want to say the next statement. The statement here is, so given that we have this continual resampling here, one might wonder, in fact, this is something we show in this paper, that in the case of these waves, we can think of that, or coarse grain these models on the right time scale, such that we can map them onto an effectively well-mixed population, but one where the offspring distribution is broad. In the present case, the offspring distribution would be described again by this rather broad, it's called Luria-Delbrück distribution or whatever. So in this paper with Gabriel, Berzou, and Kirill, we focused in particular on what we called semi-pushed waves, or let's think about pushed waves for now. So in pushed waves, we have a wavefront, and the characteristic is that the growth rate in the foot of the wave is not the largest one, but more in the bulk of the wave, the growth rate is higher, and this is kind of pushing the wave along, such that the speed of the wave is larger than, let's call it the Fisher wave speed that you expect based on the growth rate that you would have at low density. Still, however, you have a foot, you have an exponential tail here with some characteristic decay rate k, which has the properties such then, imagine now this wave traveling forward, if a mutation appears here, you can imagine that still it might have a large number of descendants on an appropriately chosen coarse graining time scale, which effectively is the mixing time scale in this wavefront. And so you can show that what one should really call reproductive numbers to honor essentially I guess this term first appeared in papers by Ronald Fisher. But effectively, it's an offspring distribution. The probability that the descendant numbers are larger than Xi decays like a power law, just like before. And you can show that, or one can show that now the exponent is given by the ratio of, so we're setting here the diffusion constant equal to 1 of the wave speed over this decay rate k minus 1. So for the case of a pulled Fisher wave, for example, this would just be 2, and then you have the equality. So this is the same distribution that appeared in the Luria and Delbrück case. But if it is pushed, if the wave is pushed, the speed is going to be larger and alpha is going to be larger. You can also describe this in other terms if you want, here in terms of ratios of the wave speed over the Fisher wave speed, you would get the exponent like this. But in light of this, then you might immediately expect that the coalescent processes in these waves should be somewhat sensitive to this alpha exponent. That's something we tested in this paper. Well, the conjecture would be given alpha and given that we indeed resample, that if we can really think about this traveling wave as continuously resampling from an effectively Ramex population that has an offspring distribution given by that, then we should be able to use Jason's results, and which he also, I think, explained in his lecture notes already, to predict what the coalescence process should be. So for the case alpha equals to 1, this is what comes up with what came up in the Luria and Delbrück example. One expect the Bolthausen-Slittman coalescent to rule, and for alpha between 1 and 2, you get a beta coalescent, and for alpha larger or equal to 2, it's the Kingman coalescent. And that's something we test in this paper. But now moving forward, I want to ask, given such broad offspring distributions, what can we say about the problem that I introduced in the beginning? So very simple setup, 2 alleles, one is mutant, we have mutants and wild type. Perhaps there's some selective difference between them. If the whole population goes through generations with broad offspring numbers, what can we say long term about the dynamics? And to address this question, I want to use a population model that's very, very related again to one that Jason introduced, but here specifically tailored to having 2 alleles. So we imagine the total population to be constant, and at time t, let's say we have a fraction xt of mutants, the red ones here. And now to generate a new generation, what I do is I draw from this offspring distribution, given some exponent alpha, for each of these individuals a family size. And I just throw them into a big ball. And typically this ball becomes very large, and the population size will be much, much larger than the one I started with. So I need to kind of cull or reduce the population. And to do that, I use now binomial sampling, right? So after in this first step, frequency of mutants would have changed to some kind of new frequency, let's call it x tilde. And to produce really the population of the next generation, I now binomially sample the success probability given by the fraction of the mutants at this intermediate step. That's now a completely neutral process so far, but we can turn on selection by saying that mutants are sampled slightly more likely by a factor of 1 plus s. So effectively what I then do, I binomially sample from this intermediate step with a success probability given by the fraction times 1 plus s. And that's how we introduce selection. And the question is what happens over time with and without selection. And is that model clear? Any question for that? Okay. So the most salient feature of the dynamics becomes actually clear from just going through this generation, so one such generation, many, many times to see what happens. So imagine we are currently in a situation where the mutant fraction is very small, just 1%. And then I draw the frequency of the next generation and see how that distribution looks like. That's shown here. So right now I'm putting myself into the situation of the Bolthausen-Slittman coalescent, backward in time alpha equals to 1. there's no selection at this point. I've chosen the initial frequency of 1% and then sampled 800 times to generate this histogram. What you see is that the distribution is actually narrowly peaked. So there seems to be a typical value of that frequency, but that peak is not at the one where I started with at 1%, but it's shifted down to a lower frequency. So there's an apparent bias. And one might wonder at first, how is that consistent with neutrality? Because we know the expectation, this was a completely neutral model for s equal to 0, that the expectation has to be at the green bar. Well, first let me state that this bias is always favoring the majority type. So right now we started with 1%, majority type gets even more usually. If you start at 99%, it goes in the other direction, so it favors the already abundant. What compensates for this apparent bias is in fact very large jumps that favor the minority type, but these large jumps are very rare. So here I'm showing the histogram on a log scale, log scale, and you see there are some rare jumps that go all the way over 50%, right? You start with 1% and the minority type after that sampling then by luck is very abundant. So these are rare, but really big. So the lesson is the rich get richer, but rarely the poor can turn the tide. And that's the dynamics that we see in this behavior. Unfortunately, for many quantities one is interested in, like what's the probability of fixation, what's the time to extinction, and so on. The rich get richer effect controls the behavior. So because that's so important, I want to give you some intuition behind it. So the next two slides are really just intuition, nothing exact at all, but I'll give you the exact dynamics after that. So that what's the intuition behind this effective bias? That we can kind of rationalize by thinking about how we go through from one generation to the next. We have, in such a generation, we have to sample from this offspring distribution for both the wild type and the mutants. And if we do that, then kind of in the sample that we're drawing, for instance, for the wild type, it's a large number. We sample very often, so we saturate more or less the histogram at very low frequency. So the histogram very much looks like the offspring distribution. But of course, there's a larger family size that we draw, X star of the wild type, which depends on how often I draw from this distribution. For the mutants, I draw less often, so its cutoff will be lower. And well, does that have an impact? Well, for narrow distributions, this change in cutoff doesn't really have an impact, but here, our offspring distribution is so broad that it does matter. So we can think about such a typical sample, right? If this is a typical sample, we can ask what's a typical offspring number. For that, we have to essentially integrate the area under the curve up until the cutoff, which for this broad distribution gives me then a logarithmic dependence on how often I sample from the distribution. N times X is how often I sample for the wild type, sorry, for the mutants. And for the wild types, it's N times 1 minus X. Right? That looks like, this is just intuition, as if the mutants have a fitness that's proportional to log to how often I sample for the wild type. That's, of course, just the sampling bias. It's not the real fitness, but it behaves like that. And this apparent fitness is larger for the wild type because it samples deeper into the tail of the distribution. In fact, if we continue with this analogy, we can now see how something like a frequency-dependent selection arises. We take here the difference between the apparent fitness of the of the mutants, which depends on its frequency, and the apparent fitness of the wild type. And you get then a selection coefficient that depends on the logit of the frequency. Yeah.
Sorry. So here, when you're speaking about apparent fitness, you mean the mean offspring number of the mutant?
it's not the mean, right? So what I'm ignoring here are rare events, right, in this tape, which are very important. This is kind of what typically happens in a typical sample.
Okay, but you're equating the fitness and this number of offspring.
Yeah, that's right. That's in this intuition. This is what I do exactly. You find that this apparent, we call it also fictitious, selective difference is proportional to the logit and scales like the inverse of log n, which is the natural time scale, the coalescence time scale for the Bolthausen-Sedman coalescent. And here you have a graph of that bias. And so then really ignoring these rare events again, the typical dynamics that you expect looks like this. And in fact, there's a sense in which this is true for the log of the frequency, but I don't want to dwell on that. I want to now give you the full dynamics, which you can show as true exactly. It has something like that. So the exact dynamics can be described in terms of the transition density, G of x naught, which is the probability density to go from frequency x naught to x in a time span tau, where tau here is the scale time. So we take here now measure time in units of the coalescence time, so that log n, we can send log n to infinity. And this transition density is controlled by two terms. The first term is exactly the bias that I've just introduced. So here you have the bias, which is characteristic for selection. But what appears there are two terms. One is the genuine selection. This is now really with selection, this little s term, and the logit of x, which is just the sampling bias that I had more or less motivated on the previous slides. And there's also a second term, which is a jump term in this differential Chapman-Kolmogorov equation. And the jump kernel has this characteristic 1 over x squared form. So it's proportional to 1 over the frequency difference squared. And that's quite different from the Wright-Fisher dynamics, if you compare it. Here again, it's the Wright-Fisher dynamics, where you have also a bias term where only the genuine selection appears. And you have a diffusion term, which we all know and love. And importantly, like in general, for a time continuous process, like the one we consider right now, you might expect actually three terms in general. One is such a bias term, one is such a jump term, but also a diffusion term. But in this limit, in the scaling limit, actually the diffusion term goes to 0. Right? So this is a then question. Okay, so you can actually solve this equation exactly for the transition density, and I'll give you some consequences about it. So the first one is, if you just think about the neutral dynamics, of course the mean. So here are many trajectories that we simulated starting from 3%. Of course, the mean has to stay roughly constant. But if you look at the median, it decays in a characteristic, actually double exponential manner to 0. And the median is essentially controlled by this sampling bias that I'd introduced. If you turn on selection, you can ask, what's the probability of fixation? Here shown on a log linear scale as a function of the selective difference. Here the dashed line is what you would expect for the Wright-Fisher case, which has here some curvature, but on this log linear scale, for the case of this broad offspring distribution with alpha equals to 1, is just exponential in S. Another one, which is I think not so easy to derive in the backward picture, is the side frequency spectrum for the entire population, which has a characteristic U-like shape. So I think the small frequency spectrum is not so surprising. There you just see the tail of the offspring distribution. It decays like 1 over x squared with a log correction. But here you have also at high frequencies an uptick in the side frequency spectrum. That's normally interpreted as a sign of selection. In fact, here you can interpret it as it looks like a selection. In fact, this tail one can show again is induced by this fictitious bias that I introduced earlier. And that's now increasingly actually seen in well, experimental populations and also natural populations. So here's the side frequency spectrum from HIV patients, which is very nicely showing an uptick. So the data are the dashed line, sorry, are the dots. And it's hard to reconcile that with a neutral Kingman-like dynamics. The same has been seen for the case of immune dynamics, and also this is early days, but I had a visiting scholar from Japan, Takashi Para, who worked a lot on these broad offspring distributions, and over the last year he has begun exploring lineage dynamics in SARS-CoV-2, and in England there's a lot of data available, so you can plot a lot of different distributions, including the side frequency spectrum, which also shows an uptick here, which might indicate or might be reflective of such a sampling bias and broad offspring distributions. In fact, Takashi generalized what I just introduced for the case of alpha equal to 1, or he tried to generalize that to the case where the offspring distribution is such that it gives rise to a beta coalescence. So alpha is between 1 and 2, to see whether the forward dynamics again is described by a bias and a jump kernel. And largely we find that true. We are unable to find exact results in these cases, but we did what we call scaling arguments. So this is certainly non-rigorous arguments in this paper, but we convinced ourselves that you can think about the dynamics in similar terms, except that now this bias, the sampling bias, actually is time dependent. For example, on short times, the bias terms kind of the sampling bias that is pulling on the median of the frequency scales in this way, depends in this way on time. So for the former case where alpha was equal to 1, you wouldn't have such a time dependence. But now that alpha is between 1 and 2, you have such a time dependence, which implies also that the median deviates from, let's say, some starting frequency x naught in a manner that is proportional to tau to the power of 1 over alpha. We think this is actually quite an interesting signal that we can look in the data, because usually you might wonder, you might expect if you have just right Fisher diffusion, that on short times you would see diffusion, so that the mean square displacement is linear in the time. But we are suggesting you should maybe look at the median squared displacement, and there you, in the case of broad offspring number, it will look super diffusive on short times. One can also obtain scaling arguments for things like the fixation probability. And the basic picture here is that if you have some genuine selection that tries to amplify the mutant population, then it will be much weaker than the sampling bias as long as the frequency is smaller than some characteristic frequency, which one can determine, and that depends on the selective advantage. And so the basic picture of how fixation works is if you start with just one individual, you have to neutrally fluctuate beyond a threshold that's of order this critical value xc, which happens with probability of 1 over n xc. And that way, then you can determine how the fixation probability depends on the selective advantage. yeah, so these are our extensions to. All right, and I'm out of time more or less, right? Is that?
Yes, sure.
Approximately, yeah. So that's not too bad actually. So let me almost summarize. There's one more picture I want to show you. Even in this case, where alpha is between 1 and 2, you get side frequency spectra that have upticks reflecting essentially this bias here, the sampling bias. It only disappears then when alpha is larger or equal to 2, where you have the Kingman coefficient backward in time. So to summarize what I told you about these jackpot events, so broad offspring distributions, they readily emerge on a coarse-grained, so on a characteristic time scale in traveling wave models. They generate a rich-get-richer effect and compensating rare jumps. And the allele frequency dynamics differs quite a bit from the Wright-Fisher case. So here again, you have the Wright-Fisher case, and here you would, I'm kind of indicating how the dynamics unfolds forward in time with selection in the case of these broad offspring distributions. I want to leave you actually with a question, and maybe one of you has an answer or is interest discussing it with me. You can imagine you have, we think of a deme here. We have a certain population here in which the dynamics is controlled by broad offspring, distribution. So imagine this is the dynamics we expect for alpha equal to 1 happening in this deme. Now suppose we have many demes that we are coupling with migration between them. And we have selection trying to push up the mutant. You of course expect some kind of traveling wave now occurring on this higher level, where the noise is now driven not by our standard kind of genetic drift, but by this jump process. I'm wondering what kind of traveling wave do you get in this case? Is it one of the standard ones that have been characterized so far? Is it going to be in the large population size limit, some kind of a pulled or pushed wave, or is it something entirely different? If any one of you has a clue, please let me know. All right, with that, I want to thank most of all Takashi, who really helped me understand these processes much better, and also with the work on semi-pushed waves. I want to thank Gabriel, who's now a postdoc at Stanford, and Kirill, who I know for a long time at Boston University. And I'm looking for postdocs. Thank you.
I have a question about how does the noise and the migration term in your last slides. So are they just interacting DIMs? But for traveling wave, one might take scaling limits and maybe like in your previous paper, look at a stochastic PD limit, like a stochastic FKBP type limit. So I wonder what might the noise term be? Will it be still just the FKBP noise whose variance is proportional to x times 1 minus x? But it's just that there's a jump there that, so
I don't know. So first of all, I don't know whether there's any continuous limit, of course, a continuous space limit in this case. I mean, here explicitly I ignored the noise due to the jumps. Of course, there's also some stochasticity there. I was kind of hoping that that would not dominate the dynamics, so I ignored it. But one should probably in general think about it.
So you mean you're ignoring the noise of moving? Of
moving, yeah. Because that seems also to be, I mean, there's a scaling limit at least where it doesn't matter for, if you do this with, where the demes behave like a Wright-Fisher model. But here, of course, I don't know anything yet.
So the offspring distribution kicks into the term, the first term there, or?
Yeah, that's here. That generates these jumps as well as this sampling bias here.
I was wondering as well, so in your model, you have a constant size population, but for your jackpot events, it seems that it's much more advantageous if you have a very small population that is growing. So if you were to have a varying size population, like that go from very small number, then back to big number and small, maybe it would increase the rate at which jackpot events occur?
Right. Thank you for the question. I mean, maybe that allows me to clarify something going back to, maybe if you think about this model here. Here, the total population size is constant, but you have, of course, these kind of subpopulations. This is kind of a spatially structured model in fitness space. In the tip of the population sizes are so small, they don't feel the finite population size constraint. They just feel it by, what matters here is the difference between the fitness of these bins and the mean fitness that's set here more or less to 0 in order to keep the total population size constant. But these guys here are growing from a small population to a large one. So there's exactly happening what you have in this Luria and Delbrück experiment, more or less, but continuously at the front. Each time you generate the next bin, you sample from the previous one, and both bins are growing at slightly different rates. That gives rise to this epsilon. Yeah, over there.
May I once again ask you to specify this additional term in the growth in the selective dynamics, this S-fic? I find this particularly interesting because I'm aware of stochastic differential equations like with alpha noise, right? But and then always with this usual Wright-Fisher thing.
Right.
Could you remind us how this S-fic looks like in a? I mean, this is coming from the sampling bias. Is this
Exactly,
correct?
yeah.
Yes.
That's
And how would a typical or a prototype form of that look like?
It's shown here, so a bit hard to see, but this is this describes the dynamics exactly in the scaling limit, and it's simply the logit of x. So it's log x over 1 minus x.
I see.
So it must disappear when the frequency is 50%, because then nobody.
Maybe not to you at that point, but to the others here. I mean, I am not aware of that kind. The only person I know who has studied these things is Bob Griffiths, for certain selection terms, right, that go beyond Wright-Fisher and some jump type of selection. This is already some years ago, and I would wonder whether this was at that time connected to something like sampling bias, which I find now very natural. Is anybody aware of that kind of SDEs? So it's again a pioneer thing.
Are there questions online?
If anybody wants to ask a question online, please raise your hand.
If not, then let's thank Oskar again.